All right, so I got cut off again from that other video. This 10-minute increments is really killing me. Anyways, so if I were to draw a vertical line anywhere on this graph, I would see that my vertical line would touch the top of the circle and the bottom of the circle. So because 2 points lie on that vertical line, it makes it not a function. So to be a function, it would have to pass that vertical line test, and this graph does not. All right, let's move into equations. Now, equations are one of the harder ones to determine the domain and range unless you have a visual. So with that being said, just because I know what this equation is going to look like, we can go ahead and draw a quick sketch of what that image would look like. So I'm going to draw off on the side here a quick sketch of the X and Y axis. And you can go ahead and do the same. So Y, and then my X going left to right. And so what I have here is I notice that my X, or my input variable, is being squared, and then I have to subtract 1. So I could go ahead and take time to make a table for this by setting up an X and a Y column. And anytime I make a table to help me graph points on the coordinate plane, I want to choose some negative values. I want to choose -2 and -1. I also want to choose 0 and then some positive values. So +1 and +2. So here, this is where we have to keep in mind our order of operations, something that we learned both in 6th and 7th grade math. So, and 8th grade. So in negative, if X is -2, what that means is instead of writing X, I would replace X with a -2. So this would mean that I am taking -2 and I'm squaring it. So I'm just going to write this down below as kind of like a skeleton. I want to find Y when X is -2. And again, I'm squaring that and subtracting 1. So order of operations would say that I have to square or do exponents first. So -2 squared means -2 times -2, which is a +4. And then I would subtract off 1. So 4 minus 1 is 3. So when X is -2, Y then, or my output, is 3. So let's, into our skeleton, put in -1. -1 squared would be +1, and 1 minus 1 is 0. Let's put in 0. 0 squared is 0, and 0 minus 1 is -1. Let's put in 1 into our skeleton. 1 squared is 1, and 1 minus 1 is 0. And finally, 2. 2 squared is 4, and 4 minus 1 is 3. So if you notice in my table, there's some mirroring going on. So if I kind of circle 0, -1, I can see on the Y column that it goes 3, 0, -1, 0, and 3. So basically, if I were to fold my table in half and 0, -1 is like my crease, these numbers match up, they mirror. So now when I plot this, again, this is a quick sketch, or what I call a quick sketch because it's not on the coordinate plane. But when I plot these values, let's see what happens. So I'll kind of just put my dashes here, and these are all by 1s to represent the coordinate plane. So 0, -1 would be down here. -1, 0 would be right here. And -2, 3 would be over here. If I go in the positive direction, 1, 0 is there, and 2, 3 is up here. So what's happening is this U shape is forming. So again, what's nice is anytime that I'm given a equation, I can go ahead and make a table, plug in numbers as long as I do it appropriately using order of operations to create a graph, a nice visual. And so now with equations, we are also going to use interval notation like we did with our graphs. So I'm going to take my green highlighter and highlight the word domain. And what I'm doing is I'm looking for all X values that work. So I notice that when I look at my graph here, I drew arrows at the top specifically because even though this is a snapshot of the graph, if we had an enlarged graph here, what would happen is my graph would get wider and wider and wider and wider very, very slowly. And eventually I could pick any X number over here on the X axis and find a coordinate point on that line. And then same thing here on the right hand side, this part of the graph would get wider and wider and wider and wider. And so as I would travel along the x-axis to larger numbers, I could pick any number to infinity, move up and find a point on the graph. So because the entire x-axis is part of my domain, we are going to say that the domain, remember, how far left to how far right, goes from negative infinity to positive infinity. So I could keep going all the way to negative infinity, find a point on that line, and eventually branch out wider here. And then same with positive infinity. So all x values work here. Now with infinity, we always use the parentheses because infinity is not a true number or a true endpoint. It's kind of like a holding number, I guess you could say. So we always use parentheses because we can't say infinity is in fact an actual number. So then finally for my range, again, I'm going to use purple. I need to see how far low does this graph go to how far high. So if I'm looking on my y-axis here, the lowest point that I see my graph travel to is this point, or that mirroring point down here. So this is the lowest point, and so that point on the y-axis is at -1. And then if I allow my eyes to travel how far high or up along the y-axis, I notice that because of these arrows, this graph is going to keep stretching further and further and further and further up. So I'm going to keep going along the y-axis to higher and higher numbers. So my domain then starts at -1 for the y-axis, and then it's going to creep higher and higher until it reaches infinity up here. So my range here, how far low is -1 to how far high is that it'll reach infinity. And again, for all infinity symbols, we use parentheses. But because -1 is part, or my graph crosses that -1 on the y-axis, I have to use a bracket. Something that's a helpful tip here is when you set up a coordinate plane, it's nice to label, because I think sometimes we get stuck that right now I only drew 3 dashes, so it only looks like there's 3 values on this coordinate plane, when actually it goes to positive infinity. So remember, this is a number line that can extend on forever. So if I extend it all the way to the right, that would be positive infinity. If I extend it all the way to the left, I'd be traveling to negative infinity. Same thing for the y-axis. If I were to extend this y-axis all the way down, I would be traveling to negative infinity. And if I extended it all the way up to the top, I'd be going to positive infinity. So labeling, if you ever in the future have to create a coordinate plane, an x and a y-axis, I would label each of those ends of your arrows as infinities or negative infinities or positive infinities to help remind you that these lines or these axes travel on forever, even though we're running out of space on our page. So finally we come to whether this this equation is a function. So if we notice here, if we look at our quick sketch of a graph, if we were to draw a bunch of vertical lines, we would see that our vertical lines would only pass through the graph once. So it would never pass through more than one spot. So that's what makes this a function. So this equation is a function because I could draw multiple vertical lines through the coordinate plane, and those vertical lines would only touch the graph in one spot. Remember, if those vertical lines touch a graph in more than one spot, then it would not be a function. So this concludes our video about how to determine and write or notate the domain and range depending on a data display or a different type of display of relations between numbers. It's going to take some time, and it's going to take a lot of practice and taking time to practice those examples in order to feel comfortable. So by all means, pause me, rewind me,